Okay, so 2.3 is something called continuity. Okay, so continuity means it's continuous. So basically the definition of continuity means that you can draw it without lifting up your pencil. So something is continuous if you can draw it without lifting up your pencil. So most examples would be of things that are not continuous. Not continuous. So if I have if there's an asymptote, so this is continuous everywhere except for at x equals 0. So this is an example of an infinite discontinuity. Continuity. So infinite discontinuity just means there's an asymptote there. So it could be like, if I could squeeze another one in here, 1 over x squared looks like this. You know, the left-hand limit and the right-hand limit both go to infinity, but there's still a point of discontinuity there. There's an vertical asymptote. Another example of an infinite discontinuity. A jump discontinuity. I'm not going to write that word again. I have a hard enough time saying it. So jump discontinuity means that it could be a piecewise function where you've got like a parabola that ends here and it becomes a line that goes down right here. So this is a jump discontinuity when you jump from one value to another value. Or the greatest integer function, you know, when it's a stepwise, like this, there's a series of jump discontinuities there. So those are jump discontinuities. Another example is a removable discontinuity. That's when they're infinitesimally small. A removable discontinuity, we've talked about those a little bit where you've got, oh, I'll do this one. Okay, so there's one point of discontinuity. You can't draw this without lifting up your pencil because there's a hole in the graph. So basically a removable is a tiny little hole in the graph. Or we had the ones where there is, well, other functions that have just a hole in the graph. So that's called a removable discontinuity. If I have a point right up here, I still have a removable discontinuity because you can't draw it without lifting up your pencil. So the function is defined at 0, but there's still a discontinuity there. All right, those are the three main ones. There's also an oscillating discontinuity. I'll squeeze it down here. Oscillating discontinuity. That's when it just starts to freak out when it gets close to a point. So I think it's like maybe sine of 1 over x. Let's try that. Turn my plot off. Alright, so sine of 1 over x. Let's see what that one looks like. I'm going to do a zoom trig. Okay, not exactly. Looks like a nice heartbreak. I'm going to zoom in a little bit more. So it just starts freaking out when it gets closer and closer to 0, and then it chills out afterwards. That's called an oscillating. So the function oscillates back and forth forever and never gets to 0. So that's called an oscillating discontinuity. It's pretty rare, but it's another type of discontinuity. Let's see, page 78. We'll see if this is worth looking at. That's what I have in my notes here. Oh. Well, let's do exploration 1 first. Alright, so this is on page 77. Okay, so it's factor the denominator. What is the domain of f? Investigate the graph of f around x equals 3 to see that f has a removable discontinuity. So you know it's a removable discontinuity if there's a factor on top and bottom that divide out. That eliminates just one little tiny hole. So spend a couple minutes going through this exploration. I'm going to pause the video and then we'll come back to it. Can I pause it?